Thanks for joining my lightning talk. My name is James Foster. I'm a research scientist with the CSIRO, and for more details about me you can see this slide. So this talk comes out of the development of a JuMP model within a project for a major Australian transmission network operator, where we were asked to provide decision support for their future planning. So this talk is about the challenges, techniques and design choices that might help others as they work on related projects and processes. Essentially about discussing a flexible JuMP-based modelling workflow for a non-specialist audience. This is not about a particular package that's been developed for others to use, though this might be a possibility. And it's not even really about energy system modelling in its own right, but more generally about the process of basing a large project around model development with JuMP. And given the nature of a lightning talk, it will be at a general level. So the model we developed represents Australia's national electricity market, interconnecting the eastern and southern states. So the model formulation was bound to a linear programming framework in order to have some control over the scalability of the model and allow custom features to be added without solve times blowing out. In the range between a full nonlinear power flow dispatch engine and a copper plate capacity expansion model, we landed at the transmission model called the transshipment grid model with capacity expansion variables across a range of technology categories. In terms of physical representation, there are 16 primary spatial zones with many more subzones, and a whole host of things shown here that parameterize certain predetermined scenario definitions, of which there were 8 developed before commencing the project. And in timescale, the model spans every year from 2020 to 2050, with each optimization solving over a 1-year time horizon, with hourly time steps subject to prior capacity values passed between solves. And a typical Groby log shows about 9.5 million rows and 7.2 million columns. Now for me, there's the two main parallel tracks to getting a working model. Model code and data code. So that is the JuliaJump code structure on the one hand and the data cleaning, loading, transforming workflow on the other. A first initial challenge to conceiving a model, somewhat independently of the modelling language, is to develop a coherent formulation of relevant model objects at a sufficiently detailed resolution without creating an effectively intractable situation, especially when the need to scale arises. A typical example in choosing a spatial aggregation that allows constraints to be written with variable terms that are of a relatively comparable size. And the central constraint or set of constraints in energy system modelling is often to do with the energy balance, where for each time step the sum of energy supply matches the energy demand. So one technique to start with this is to start with the central piece or constraint and work outwards in developing the rest of the model. A big help in model code development and structuring might be to adapt an existing model. In my case, I started by adapting the open source model Data, and which has been through a process of refinement and already used in a research context. My advice here is to draw on the experience of others as much as possible, hopefully via open access, knowing that the process of public release should have refined the model and the code implementations. And you can hopefully contribute back to that project as well. So the next challenge is for having a working model is the integration of scenario-dependent datasets in order to correctly form the model instances. Now, flexible design was required to allow for potential expansions in scope of the model, including new data inputs and data dimensions, along with model additions, all without creating a workflow that's so complex that reasoning and debugging would become highly difficult. One axis of approach to this was a literal modularization of code. So creating core modeling data structures in one package, which we call data.jl. Thanks to Mario and Wolf Peter for sharing an early port of data from GAMS to JuMP. And also acknowledge the data structure code in Power Models. So on top of this module for core model formulation, we used a configuration module called stable.jl for framing and configuring the hierarchy of settings needed to define a given yearly instance within a run, within a scenario. So this enables a single set of locations for configuration, essentially a single source of truth that persists across model runs. The most basic level is to essentially mirror hierarchical JSON configuration files in code, allowing inheritance for more general settings from higher levels. Now, both these modules are then loaded, and then the domain-specific knowledge and logic is coded into Julia within a scripting repo at the very top level. And this is where we join the data with the JuMP modeling code and then perform the computations and the outputs. So coming at the problem with the parallel data track, the necessary data is compiled from verified sources and our internal analyses. The main point is that our data workflow needs to be targeted to a data consumer, which in this case are the JuMP sets and parameters needed to form a large-scale linear program. The challenge at this point is to reliably and correctly provide data for parameters that are sparsely indexed by spatial location, energy, technology type, process, even apart from the timestamp indexing. And the main tool here is to minimally transform input data into SQLite tables, so cleaned up but not in final form, to make the JuMP model yet. The transformation heavy lifting is done by a combination of SQL select commands and loading to data frames and making good use of the great data frames matter package for filtering, extracting, mapping to parameters against our sparse indexing in our JuMP model. So all this enables the workflow to be reproducible and recordable with scripts. It saves effort and more importantly reduces errors when raw components need updating, and this provides orthogonality of data with respect to the model. So the final challenge was to scale up the model to span every year from 2020 to 2050, with each solve over a 1-year time horizon with hourly time steps and capacity linking between solves. The scaling had to factor in large variations in demand from hydrogen electrolysis, generation ramping constraints, and issues around bounds being too restrictive in the scaling. We also had a manual iterative process around transmission design. So my experience here is that scaling up your model will present issues of a different nature than the model design phase, so give yourself plenty of time and a sufficient set of inspection tools for this part of the process. And I want to acknowledge here the great response to questions and issues sent via Gitter, Julia, Discourse, and of course the JuMP GitHub page. Thanks for responding. Some outstanding questions do remain for me. For instance, I did require building the model each time, and after serializing the results, it was necessary to delete the complete model structure in order to manage the memory requirements of the model. I would like to expand integration with the wider Julia energy system modeling ecosystems. For example, powersystems.gel, for example, for getting a consistent data API for building other models on top of existing data structures. And I'll just finish with some final thoughts. It's wonderful to have the full Julia ecosystem on hand to work with, coming from a situation of piecing together a mix of Ample and MATLAB with shell scripts. And I would say that if you're stuck, it's likely that you can, if you can put a minimal working example together, you'll find understandable cause and you'll be halfway there. You will often learn a lot about your modeling assumptions when designing such an example. So I will conclude by saying that overall the project met and exceeded initial expectations from the client, and I want to acknowledge those who contribute to JuMP and the Julia ecosystem, who really are partners in making all this happen, and thank you for that.